here. It's got double bond to a nitrogen. That's got some other stuff on it, right? This is a specific type of imine. It's called a hydrazone. We can make another specific type of imine. All we have to do is pick a different primary amine, right? How about hydroxylamine? We can make another type of group called an oxime by reacting hydroxylamine with some aldehyde or ketone. Let's use an aldehyde this time. We'll use a simple aldehyde. Right? Just ethanol is fine. We're going to use hydroxylamine. So the amino part and then the hydroxyl group. There's hydroxylamine. Under acidic conditions, we're going to get what? You always start there for your imine, right? And then what do you get on that? Well, the nitrogen can only have 3 bonds, right? Unless it has, unless it's going to have a formal charge. But for no formal charge, we've got 3 bonds on the nitrogen and a lone pair. So this reaction is going to happen just the same as the other two. And the first step, well, let's just start out with our protonated carbonyl. That's the first step, right? So we deprotonated the acid, and now our nucleophile is going to come in. The nucleophile is going to attack the carbonyl, dump electrons onto the oxygen, and we're going to get our tetrahedral intermediate. In solution though, so I didn't show that very first step where we protonated the carbonyl because we've already shown that twice, right? But we have our conjugate base floating around because that's where the hydrogen came from, right, off that acid. So we take our conjugate base, there you go, dump the electrons back onto the nitrogen. This is our little proton shuffling. What do I get? Now in solution, I just generated my acid again, didn't I? So I'm going to protonate the hydroxyl group so I can make water as a leaving group. And I get this down here. And draw this a little bit more suggestively so that you guys can see. I've got my conjugate base because I just used that as I used the acid, right, to protonate the hydroxyl group. So I've got its conjugate base here. Now these electrons are going to come down, form that carbon-nitrogen double bond, and water is going to leave. What are we left with? Our oxime. So up here, we've got hydroxylamine, and here I have an oxime. We have another example, last example that I'm going to show you for reacting primary amines with ketones and aldehydes. We can take a semicarbazide, azide, right, or azo, that's nitrogen containing. So if you see azo or aza or azide, you know there's a nitrogen somewhere in there, right? We're going to form a semicarbazone by reacting a semicarbazide with a ketone or an aldehyde. So let me show you what that looks like. Let me grab, let's do benzaldehyde this time. So here's benzaldehyde. And this right here is our semicarbazide. Looks insane, huh? And under acidic conditions, so catalytic acid, I'm going to make a semicarbazone. Again, carbon double bond nitrogen, right? So this right here is this right here. There's a lot of nitrogens in that thing. I know it's probably hard to keep track. But this is a semicarbazide. See, azide, nitrogen containing, and this is our semicarbazone. And again, so the mechanism for this, it looks just like the same thing we've been doing. So let's start out with our benzaldehyde. I'm going to start out with it already protonated, ready to go. We used our acid to do that. And I'm going to take the nucleophile. Now, you might be sitting there going, why are you taking the nitrogen, that particular nitrogen, to do the attacking? They all have a lone pair of electrons, right? Everybody's got a lone pair here. Why am I using that nitrogen? The two nitrogens that are right next to their flanking the carbonyl, right? Those particular electrons can be delocalized up into the carbonyl, right? And so those are just a little too close to what we call an electron withdrawing group, meaning those electrons, those lone pairs on the nitrogen, are not necessarily as nucleophilic as these. These are just a little bit farther removed. So we're going to use these electrons, so that particular nitrogen, and I make my tetrahedral intermediate here. Go ahead and draw all four things. So we got our hydrogens, and then the rest of this thing. I've got the conjugate base from the acid that I used to protonate the carbonyl, and I can take that hydrogen, give the electrons back to the nitrogen, and again, what do I get? But I've also regenerated my acid, haven't I? So I'm going to stick that over here. And we're going to protonate the oxygen. What do I make? Water. And then I've got this down here. Forgot that hydrogen over there. So here is this hydrogen, and we got the rest of this molecule. And we've got our conjugate base back, which is going to come and take this off. And we're going to eliminate water. So we're going to take that hydrogen. Those electrons are going to fall down here between that carbon and that nitrogen to make the double bond. We're going to eliminate water, and we get our product. There's our carbon, double bond nitrogen, right? And then the rest. of what was attached to it. And 1 unit of water. The same old mechanism, just, every single time with these ketones or aldehydes and some kind of a primary amine or something that can behave like a primary amine. What about if we took a ketone or an aldehyde and we allowed it to react with a secondary amine? What do you get? So say, for example, I took some kind of, you can just use this again, I guess. This ketone, so cyclopentanone. But now I'm going to react this with a secondary amine instead of a primary amine. What do I mean by that? I mean, I'm going to have 2 R groups on the nitrogen. So it can have 1 hydrogen, right? And we're going to use a catalytic amount of acid. And we're going to make a new piece of functionality. Now, you're probably sitting there going, well, what are you going to do? You have 2 R groups, right? It's not like we're going to deprotonate a second time, right? And make that double bond. Nope, we're not. But we can deprotonate that carbon, kick the water off, and we make what's called an enamine. So ene, because of the double bond, and then amine. This is a secondary amine. How does this happen? Same way the other reaction happens, right? Only this time, instead of grabbing that extra hydrogen, because there isn't an extra hydrogen, we're simply going to deprotonate the carbon next door so that we can kick the water off. I'm going to start with this already protonated, save us a step, right? And then we're going to attack with our nucleophile. Our nucleophile is going to be our secondary amine. And we're going to take these electrons, attack the carbonyl, dump electrons onto the oxygen, and what do we get? So we've got our positive charge on our nitrogen here, 2 R groups, and we've got our conjugate base because we used the acid to protonate the carbonyl. Same old thing is happening again, right? We'll make our acid back again. HB. And we're going to protonate the hydroxyl group to make a water. That can leave. But here's the thing. At this point, before, you guys, there's another hydrogen on that nitrogen, wasn't there? Now there isn't. But guess where there is? There's 2 right here, or on the other side, take your pick. So this base is going to come and take one of these. These electrons are going to form a double bond here and kick water off. And you might be sitting there going, why don't you kick off R2N minus? Because it's too basic. Water is going to leave instead. And there's our enamine. So you might want to get familiar with just a generic enamine, a generic oxime, semicarbazone, and these are all examples of imines, right? And a hydrazone, so that you can actually pick these out. The piece of common functionality is going to be that carbon-nitrogen double bond. It's what's attached to the nitrogen up the top that's going to change things up for us. So the oxime is going to be a carbon doubly bonded to a nitrogen, right? and that nitrogen is going to have a hydroxyl group on it. The hydrazone is going to be a carbon doubly bonded to a nitrogen, and it's going to have some sort of amino group on it, right? The semicarbazone, again, the carbon doubly bonded to the nitrogen, and then there'll be this weird sort of like urea-looking thing hanging off of the other side. So, and then the enamine is really easy to spot. The enamine is just that double bond, and then the carbon is singly bonded to a nitrogen with a couple of R groups. So that you get that when you use a secondary amine and reacting it with either a ketone or an aldehyde. I am going to prepare a lecture for oxygen-containing nucleophiles. You're going to notice the mechanism is very similar. We're going to be activating the carbonyl, right, attacking with the nucleophile, doing a couple of proton shuffles. We're going to eliminate water, and we're going to, boom, have another piece of functionality. So we're going to introduce acetals, hemiacetals, and then ketals and hemiketals in the next lecture.